Hello everyone and welcome to my video on exponential models and applications. Yes, I did read it. My name is Darren from Maths Guru. Thank you very much for joining me. Hopefully this video is going to be mind-blowing. Well, I can't promise, but I'll do my best. Now, if you want to download lesson notes, they are all on mathsguru.com. You're going to say, I say mathsguru.com, where there are, as I say, all of these videos, downloading lesson notes, VCAA, exam questions, and so much more. It really is quite good. Now, what are my learning objectives? Well, hopefully to understand there are a number of real-world applications relating to exponential growth and decay, and to understand how to use each to answer a range of varying questions. And we sort of diverge a little bit away from the sort of standard y equals 2 to the power of x into some pretty interesting real-world applications. Now, before I go any further, if you can subscribe, that would be awesome. Subscribing to my YouTube channel just lets me know that people out there are watching this content and finding it useful. And of course, please leave a comment, let me know how I'm doing, and obviously tell your mates and your teachers as well, which would help sort of grow the channel. Thank you. Right, this is actually the final section in the course, which is going to build on all of the work that has been covered previously here in the Methods 1 and 2 course. And again, don't worry if you haven't been doing Methods 1 and 2. This stuff is universal around the globe. Right, we're now going to put it into real-world questions. And as I've said so many times, Methods 3 and 4, one of the papers has 60 marks given to application questions. That's 60 out of 80. Right, that significant proportion of that paper is about taking all of the information that you have, all of the learnings you've done, and applying it to real-world questions. Okay, and my mathsguru.com has the Methods 3 and 4 course there as well. Right, exponential growth and decay. Now, in general maths, we get very tied up on the idea of what exponential growth is. I'm not going to get too deep into that in here, but at this moment in time, if we have something of the form y equals a number to the power of x, it is going to be exponential growth. All right, and so in this situation, it is growth because as my value of x is increasing, or whatever's on my x-axis, my value of y is increasing as well, but it's increasing at a much faster rate for each value of x. That is exponential growth. All right. Exponential decay, well, obviously in this situation, as my x value is increasing, my money or whatever is looking at there is decreasing as well. All right, now in this situation, that would have sort of a negative value of my power, y equals 2 to the negative x, for example. Now, that hasn't made a huge amount of sense. There is a video previously in this section that you can watch about exponential growth and decay. This is now sort of going to be applying it. Now, there are real world situations where we can do this, and so there is a general form for exponential growth and decay, which I think is quite important to look at. Now, here, an amount after a set time t. So we should now be in a situation, if I was going to plot this on a set of axes, that we would know from the equation that that would be my a, and this would be my value of t. All right, so what is this value of a0? Well, hopefully from the work we've done previously, we would know that that was our start value. That would be our initial value when t equals 0. And again, from basic exponential rules, if t becomes equal to 0, b to the power of 0 would be 1. And so my initial value would be equal to a0. So in this situation, assuming that t is positive, then my graph would be here, and that value there would be a0. He says doing a superscript, not a subscript. So there we go. Yep, so a0. And what is b? Well, b would be that rate of 2 to the power of, 3 to the power of, 4 to the power of. Just means it's getting faster and faster and faster, growing faster and faster and faster. So knowing that, we can start applying it to cell growth, for example. So again, taking my information here, this is for cells which effectively subdivide. Right, now by that we could be talking about human cells, which for every period of time sort of double in number. So you go from 1 cell to 2 to 4 to 8 to 16 to 32. Now what's important here is n is the number of cells at a given time. So that t there is my time. N0 would be the number of cells we started with at a time 0. And again, it doesn't have to be a time 0. And the one here, this TD is really, really important time. It's the generation time.